Welcome to the next story in the larger story of biomolecules. I think this would be the last lecture or last story in the biomolecules where we tie up all the loose ends and so on and so forth. We will begin the story by asking this question: how are proteins and of course enzymes, we are looking at enzymes that are proteins, made in the cell? To answer this, I would point you out to a required video here. I think the video in the list is number 18. It is a very interesting video, an important video in terms of the principles for the course. So, I would require you to see that video. Please see that video. It is only about 3.5 minutes long. Okay. It is made nicely. It was made as a part of the human genome project, but it very nicely explains how proteins are made. Okay. Very briefly speaking, this video will say that the information in something called the DNA, deoxyribonucleic acid, gets converted or transcribed to the information in the messenger RNA, and that gets translated to the information in the proteins. That is the base message in this particular video. Please take a look at it. It will provide you with a nice context. It will probably clear up quite a few of those nagging questions that you may have had at several points in time and so on. Okay. It is a very interesting aspect of life in general. So, we said that the information in what is called the DNA, deoxyribonucleic acid, gets converted to information in the mRNA. Okay. What exactly is DNA? Okay. All of you, I am sure, would have heard of DNA. It is a very popular term nowadays, and that is how information is stored in the cell, the information that needs to be passed on from one generation to another generation. Okay. In fact, DNA is the code through which this information is passed down generations. So, what is DNA, and how does the structure of the DNA make it possible for information to be passed on? Okay. DNA is a polymer of the monomer called a nucleotide, deoxynucleotide, but let us call it nucleotide here. If you look at a nucleotide, it consists of 3 major parts. You have what is called a pentose sugar here, a pentose carbohydrate here. This is an oxygen, 1 carbon atom, 2 carbon atoms, 3, 4 and the 5th carbon atoms here. Okay. So, this is called the 3 prime position, this is called the 5 prime position of the carbon atom, and to this 5 carbon sugar, to the first position, you have what is called as a base, a nitrogenous base that is attached to it. The combination of the base and the pentose sugar is actually called a nucleoside. To a nucleoside, if you add a phosphate group, it becomes a nucleotide. Okay. And this is the base unit for DNA. Repeating, you have a pentose sugar, you have a nitrogenous base that is attached to this, and you have a phosphate group attached to this, you get the monomer of DNA, which is a nucleotide. So, you can see here, this is the pentose sugar, the nitrogenous base and the phosphate group. Okay. So, this, let us start here, the pentose sugar, right, and the nitrogenous base and the phosphate group. 2, this is a 3 prime which is end which is free here, the 5 prime end of the sugar is attached to the phosphate group. The 3 prime end of another sugar, ribose sugar of a nucleotide gets attached to this phosphate group, and that is how the chain gets built up, the polymer gets built up. Okay. So, you have one 3 prime end that is free, the 5 prime end attaches to the 3 prime end of the next nucleotide, similarly the 5 prime end attaches to the next, to the 3 prime end of the next nucleotide, and so on and so forth, to form the polymer of DNA. The bases, right, we said that it contains a sugar, the base and the phosphate group. The bases are of 5 kinds. They could be cytosine, thymine and uracil, or adenine and guanine. Okay. Some of these terms would be familiar to you. These are what they are actually. You could have pyrimidines, which are just one ring nitrogenous substances, and purines, which are slightly bigger nitrogenous substances. Okay. So, this base here could be one of these kinds, either a cytosine or a thymine or a uracil or an adenine or a guanine. Okay. It so happens that in DNA you have only CTAG, okay, Gattaca, remember, CTAG, and in what is called RNA you have the uracil instead of thymine. The pentose sugars are of two kinds. DNA has what is called a deoxyribose, and RNA has what is called a ribose. Okay. The only difference between these two sugars is the 2 prime position. In the case of deoxyribose, you have a H in the 2 prime position. In the case of ribose, you have a OH in the 2 prime position. That is the only difference between or that is one of the major differences between DNA and RNA in terms of the sugar here, right. Okay, let us go back a little bit. So, you have a nucleotide which could be a DNA or a RNA, you have a pentose sugar. If you have a deoxyribose sugar, you have DNA. If you have a ribose sugar, you have RNA. In the case of a base, you have, if you have adenine, thymine, guanine, cytosine, those are the bases found in DNA. You have adenine, uracil, guanine, cytosine, then you have the bases found in the RNA. The phosphate group, of course, is the same. So, that is what a nucleotide is all about, and that is what passes on the information from one generation to another. One of the reasons, one of the ways by which information transfer from one generation to the other is made possible is through this. This is adenine, this is thymine, right. You have the adenine and thymine represented here in part, you have the sugar attached, then you have the nitrogenous base alone shown, and then of course, you have the phosphate group which is not shown. Adenine, thymine, if you go back, adenine is here which is a purine, thymine is here which is a pyrimidine. Okay. Adenine and thymine, by their very nature, by their very chemical nature, can form hydrogen bonds between these two. Okay. There are 2 hydrogen bonds that are formed between adenine and thymine, and this is what is called base pairing. Okay. Nitrogen is base, base pairing. This is a base pairing, a hydrogen bond formation between adenine and thymine. There are 2 hydrogen bonds that are formed between adenine and thymine. And guanine, cytosine, okay, guanine is a purine, cytosine is a pyrimidine. You have 3 hydrogen bonds that are formed between cytosine and guanine. Okay. So, this hydrogen bond formation or base pairing, as it is called, is what gives DNA its structure, and it makes it possible to do what it does. How is that happening? Let us look at one strand of the DNA here like this. Let us look at the other strand of DNA here, that is like this. We know that adenine pairs up with thymine and guanine with cytosine. The guanine on one would pair with the cytosine, adenine, thymine, guanine, cytosine pairing, and this pairing gives the dual strands of the DNA a helical structure. Okay. So, this is what automatically results because of the various constraints in size and so on and so forth. The base pairing or hydrogen bonding between the bases gives it its double helical structure, and the double helical structure makes other things such as replication of DNA as well as transcription, translation and things like that possible, that we will see in later lectures. Okay. So, this is how the double strand is getting formed here, and this double strand becomes essential for its various functions. The DNA in a single cell, if you stretch out the DNA, can be about 2 meters long. Right. The 2-meter long DNA is somehow packed into the nucleus, which is micron sized. Okay. The cell itself we saw was the bacteria in a eukaryotic cell, let us say a typical size is 10 microns, right. The nucleus is much smaller than that, and in the nucleus this DNA gets packaged. Right. Whatever is 2 meters long when stretched out gets packaged there. How does that happen? That is because the DNA is in a coiled form. Okay. You can imagine this, you can take a piece of string, okay, cotton string, and try twisting it, then it twists and twists and twists and twists, and it becomes smaller and smaller and smaller. Okay. That is pretty much what happens with DNA too, and the coiling and supercoiling and supercoiling around proteins which are called histone proteins essentially results in it being packaged into a size that can fit into the nucleus. And so, DNA exists in what is called a chromatin form, which is nothing but this coiled form. Okay. Chromatin condenses even further to form visible chromosomes, colored substances, during cell division. In other words, they take up dyes during this stage, and that is why they are called chromosomes, colored bodies. During cell division, chromatin condenses further to yield visible chromosomes under, of course, the microscope, not to the naked eye. Okay. Please take a look at this video, DNA and chromatin, which gives you the details of this packaging. It is an animation, which is a nice animation which shows you how the 2-meter long DNA gets packaged into a nucleus by coiling and supercoiling around histones and other proteins. Okay. This is the video is number 19 here. Please take a look at that video. Now, let us look at a slightly different aspect. We said cell is the fundamental functional unit of life, and it is a very busy place. A lot of reactions happening all the time, thousands of reactions happening all the time. There is transport of substances into the cell, out of the cell, and so on and so forth. We already saw lactic acid going out of the cell, and so many things happen there, and any process requires energy. So, how does the cell get the needed energy to do all these things and maintain life? This happens because a large amount of energy in glucose, okay, if we split glucose or if we oxidize glucose, a large amount of energy gets released at one time. The cell may not be able to use all that energy at that time. Therefore, it requires energy in units that it can use directly, right. So, that is what happens here. The large amount of energy in glucose gets packaged into appropriate energy in what is called an adenosine triphosphate or ATP. ATP you would have heard, right. This stands for adenosine triphosphate. This happens to be the energy currency of the cell, and this process happens through what is called a substrate level phosphorylation of ADP or an electron transport phosphorylation of ADP. We will look at a little bit in detail about these things, and this is how the cell gets its energy to do its various functions. Please take a look at this video to get some idea. It is a slightly longish and an old video, but I think it is a nice video which gets to all the which touches upon all the necessary aspects for an introductory kind of an exposure. Please take a look at it, it is about 9 months long. And we said ADP getting converted to ATP and so on and so forth, adenosine diphosphate getting converted to ATP. It so happens that ADP and ATP are nucleotides. They have the structure, a sugar, a pentose sugar, a base and a phosphate group or phosphate groups attached to it. So, a ribose sugar in this case ATP. Okay. So, this is somewhat closer to RNA, the ribose OH in the 2' position. The adenine, okay, ATP, adenosine triphosphate. So, the adenine nitrogenous base, it is attached to the first carbon atom here, and the attachment is not shown, the bond is not shown here. This one needs to be removed and this bond needs to go and attach to nitrogen here, and to the 5' carbon, oxygen and so on, you have phosphate groups that gets attached. If you have 2 phosphate groups, then this is called adenosine diphosphate, okay, ADP, and if you have 3 phosphate groups attached, you have adenosine triphosphate. So, ATP and ADP, the energetically important molecules in the cell, are also nucleotides. ATP gets converted to ADP by the release of energy, and this energy is rightly sized, right, to carry out, to fulfill the needs of various different cellular processes, reactions maybe and so on and so forth. So, it is about 7.3 kilocalories per mole, and that is about the right size for various things. ADP gets converted to ATP, and that is what we are going to, that is how ATP gets formed, and that would require input of energy. Okay. So, ADP getting converted to ATP to kind of store up the energy currency, and which is ATP 3 phosphate molecules. A breakage of this would yield energy that can fuel or that can provide the energy for the various cellular operations. So, let us look at this process in some detail, ADP getting converted to ATP. ADP getting converted to ATP we know is by addition of a phosphate group, it is called phosphorylation. Phosphorylation of ADP yields ATP, and dephosphorylation of ATP yields ADP, and it is this dance that provides the energy for various things and also makes the energy currency in the cell. This phosphorylation of ADP to ATP is carried out by 2 major means. One is called substrate level phosphorylation of ADP. The phosphate group is transferred from a metabolite to ADP and is the process is mediated by an enzyme, that is what is called substrate level phosphorylation. Let us say a phosphate molecule can get dephosphorylated, and in that process provide the phosphate group to ADP enzymatically to create ATP, right, and that is called substrate level phosphorylation of ADP. We are not getting into details of this, there is a lot that can that one can know about this process, we are not getting into this. However, it might be helpful to see these videos if you are interested in knowing some details. So, I would say that this is kind of optional videos. The electron transport phosphorylation of ADP, right, the energy of the hydrogen ion gradient across an integral membrane is used to add phosphate to the phosphate group to ADP to form ATP. This by itself is a very, very interesting process. This was what Mitchell proposed I think in 1966, which won him the Nobel Prize, which provided the coupling between the hydrogen ion gradient and energy which provided the a way by which ATP can be made, which was kind of missing at that time. He proposed this as a hypothesis, and it explained a lot of things. Okay, it won the Nobel Prize also. So, it is that important, and you could look at these 2 videos to get some more insights about electron transport phosphorylation. Okay. These are details, I do not want to get into details in this introductory course. However, if you are interested, you can get into these by yourself. So, to sum up, there are 4 fundamental biomolecules from last to the earliest: nucleic acids, DNA, RNA, ATP and so on, proteins, polymers of amino acids, carbohydrates, sugars, lactic acid and so on that we have seen, and lipids, which are membrane components, oil, butter and so on, right. So, these are the 4 fundamental biomolecules. All life is made out of these biomolecules, and the structure function relationship is important in these biomolecules, many of these biomolecules, and that is what determines life itself. That is why we were so interested in knowing about these 4 fundamental biomolecules. Now, we are going to wrap up everything together, and by coming back to our original story, which is curd formation. Why does curd form? We said acid formation followed by protein aggregation. Protein that we are looking at was casein. Let us look at the protein aggregation to a certain extent. We took off on side routes, and those turned out to be very enriching in terms of knowing about fundamental biology, biological molecules and so on. So, let us come back to our initial story and finish up there. We have water here, H2O, and there is hydrogen bonding between water molecules that we know now. A small part of it is ionized at any time into hydronium ions H3O plus and hydroxide OH minus. Okay. And a very small part, 10 power minus 7 is what it is, and that is why pH is 7, negative log of the hydrogen ion concentration, right. So, that gives you an idea as to the concentration of the species that is dissociated, and this happens naturally, and this is what gives water its pH. So, this is what happens. When acid is introduced into the medium by the cell, the medium pH goes down further. The hydronium ion, hydroxide ion concentrations vary. H plus, which forms hydronium ions, and therefore, this starts going up, the pH starts going down. The protein solubility is pH dependent, because the net charge on the protein is pH dependent, right. You know that the charges on the protein, this is zwitterionic molecule, therefore, it is pH dependent and so on. And at various different pHs, the net charge in the protein could be very different because of the nature of the amino acids that make up the protein. Therefore, the way it interacts with the hydration layer, we said that if a protein is dissolved in water, there is a hydration layer around it. The interaction with that hydration layer changes with charge, changes with pH. Okay. At the isoelectric pH is the pH at which there is no net charge. The interactions would be very different, and at that time the interaction between the proteins could be higher. So, they fall out of solutions, there is no longer much of the hydration layer around it, therefore, they fall out of solution, they aggregate because of the interactions between them, and that is essentially what happens. Protein conformation may also change with pH, and it can no longer be in solution. Therefore, the casein molecules there, the casein protein molecules there have different interactions with their hydration layer. At one point in pH, they came out of solution, they interacted with each other and they curdled, and that is how curd gets formed, right. So, this is one of our base stories with which we started out. So, let us finish up there. The take home message is something that we saw earlier, the 4 major kinds of biomolecules. The very nature of the biomolecules gives it a certain amount of function. The way they are put together, the structure gives it its major function and so on. Okay. And of course, we started out with the fact that there are a large number of microorganisms, and there are ways to organize them to make better sense of them, right. So, that is the story on biomolecules, that is the module on biomolecules, and when we meet up next, we will take up another aspect. See you then.